Hey, oh no, class is still over. Class is back on. I see we got a lot of questions here. Thank you, Mohammed, Matthew, Josephine, and Kylie right here. We're going to do them in order right here, so we should be able to get to some Chapter 7 homework. Let's go ahead and take a look at question 8 and 474 homework. You bet, Mohammed. Let's go take a look. I'm going to grab a little bit of help right here. This is the clustering homework, I believe. Pulling up the clustering homework as we're speaking right now. Due coming up here soon. It's due tomorrow. Wow, that's soon. Let's go take a look. Getting the homework up and loaded. And this is question 8 for 474. Let's go take a look and give some tips right here. Let's go take a look. Here we go. Looking at the cluster center for the 3 cluster schemes, the only obvious one's cluster defining characteristics is baby. So when we get clustering schemes, what do our clustering schemes have in them? Like, what are these values right here that we're seeing when we have a standardized metric? So, Mohammed, what do we have? And we'll circle back here doing some more later. We do some Chapter 7 coming up. You bet. What are these values right here that we're looking at, Mohammed? So what are these values in clustering schemes? By exactly, great job right there. 100 points, everyone. Mubot, you awake? He probably is not awake. He said, no, I'm not awake. And so let's re-wake up Mubot. Mubot, wake back up. He breaks the world. And so these are z-scores. So that's a very unusual observation for that group. Though it's clear the clusters 1 and 2 are distinct groups since the signs of almost all columns are opposite. So we've got like some above average customers. We got some below average customers. Look at the centers for the floor cluster schemes, identifying which clusters 1, 2, or 3 has split into 2, and comment on whether our understanding of the households increases from going to 3 to 4 clusters. At this point, we'd try out 5 clusters because here's what we do. This is the key thing with clustering. If 3 clusters work, we check out 4. If 4 clusters work, we check out 5. If 5 clusters work, what would we do? So fill in my sense right here. If 5 clusters were to work, like if we're like, oh, 5 clusters is a great scheme, what would we do then? What would we, if 3 clusters work, we'll look at 4 to see if it's good. If 4 clusters work, we'll look at 5 to see if it's good. If 5 work, we'll look at what to see if it's good. Well, that's kind of the answer. Basically, you just keep going. If it keeps making sense, you say, well, then this is a distinct group. Exactly right there, HTT, we'd check out 6 clusters. So that's the process. Keep adding more clusters if it looks good. And just to see what you get, be like, well, does adding another cluster help? So we want to see what happened to these clusters right here when we go to 3 to 4 clusters. And so let's see right here. Identify which cluster 1, 2, or 3 has been split into 2 from 3 to 4 clusters and comment on whether your understanding increased from 3 to 4. So to see if things change from 3 to 4 clusters, and we're just going to call this Q8. You can then navigate to this pretty quickly. We got now a Q8 chunk. This was the add chunk button, and now we have a Q8 chunk. What you want to do is you want to go to your, I believe, if we have a k-mean scheme in here, and let me go right here. This is not what we're going to be doing. Let me go get the k-means, and let me load in the Kroger data. This is very clearly my answers will be wrong right here because there's more work that needs to be done into scaling, transforming the data, put everything on an even playing field. So we're just jumping to this. My answer is going to be very, very wrong right here. So with the k-means algorithm right here, looking at the clusters or making clusters, we have not scaled our data. We have not transformed our data. This is a bad idea. Like I want to be like, bad idea. I am not doing this correctly. I'm just doing it. So centers equals, let's go 3. And let's go end start, which is the number of times we have to restart the algorithm to refine the centers. We'll go 20 restarts and max iter, which is the number of times it'll iterate. Oh, it's iter max. Iter max, let's go 20 also. It might give you different parameters, so make sure you use those. K3, and let's go here and call this K4. And let's call this K5. So we've actually just done the k-means algorithm, and that's what you should try to do is copy paste your code. And now you've done k-means with 3 cluster centers, 4 cluster centers, 5 cluster centers. It's just that easy to rerun the algorithm right here. Now, if you want to know how things are assigned, we would go here to the K3 list and go to the centers. No, it's not what we want. We could look at that. Let's go to cluster codes. There's the cluster codes. And now we're going to take the K3 cluster codes and go to Kroger data. I'm just using the Kroger data. And I'm going to go on it, $sign. I'm going to go to K3. And now I've assigned the cluster codes with 3. And now I've assigned the cluster codes with 4 and 5. Does this make sense? What I'm doing right here, Mohammed, is I'm adding, and also HTT, is I'm adding cluster codes to the end of this right here. You can see some of the changing of it, especially if you go look at the data. You can see where the cluster codes are, and you can see not everything's staying the same, whether you use a 3 cluster scheme, 4 or 5. Eventually, we'll start to see numbers bigger than 3 here. At some point, we'll see a number bigger than 3. Really? Did I not Ooh, should. Let's go take a look at that. If we want to see what's going on right here, it's just, well, did it? Oh, no. Muhammad, 100 points right there. Yeah. Yeah, I was like, eventually we should see that. Let's take a look at it now. Oh, look at that. Look at that. I was just seeing if you're paying attention right there. I didn't change. Now we can see a 5 max cluster, so it's going to cluster up to 5. We would have saw it with our table output too. I just didn't change that right there. So when we look at this, if we go to a table, going to our Kroger and going to the K3, you can kind of see how things are split apart. Oh, wait, let me do it in order. Okay. So all I'm doing is looking at tables of this, and you can see right here, we have right here 383, 1606, and 11. And then when we get down here, we have a group of 4, which is rather interesting. And it looks like it's split differently this time. This one's not quite the same as yours. We didn't have a group split apart, but here's where 4... Oh, look at this. Cluster 4 in this instance was reassigned to cluster 1. And that's only the real thing I see staying the same right here. Yours should look a little bit easier to read than mine. Mine doesn't have an easy pattern. But my cluster right here... The cluster scheme didn't simply resplit, because you will sometimes get where you have one cluster is broken off into 2 components, and you will see that in yours. But does that make sense? It seems logical right here that these 4 points have moved over. Good to see you here, Ivy, into this section right here, and then we have some maybe reassignment of clusters as you go through this process. So if you want to look at your cluster centers, you could go to your K3 algorithm. We should be able to look at the centers right here. And this is the means for the clusters. So you can kind of get an idea what's going on. If your data is scaled, you'll see z-scores here, which you probably should. And you can see right here the cluster centers 1, 2, and 3. We could go right here and look at for 4 clusters. And here's the cluster centers for 4 clusters. Did we rerun the data with this? K4? Why are the cluster centers right there? Weird. Weird things are happening. Let me rerun the K4 data. And let me take a look at that and resave this in here. And then let's go ahead and look at the centers for 4. Ooh, it's got some weirdness. I don't know what's going on right there. Well, the cluster centers look a little bit different. But we see right here the cluster centers with 4 cluster centers. And we go up to the 5 cluster centers. I think that's a little bit weird. Oh, I think it's doing it over the... Yeah, having a bit of an issue right there. But we have here the 5 cluster centers right here going for the means of each group, and we can see what's going on with these groups. Is this making sense, Mohammed? I don't want to give away the answers, but I want you to be looking at your values and thinking about which groups we have right here have split apart. So you can look at a table. So that's kind of the code right there to look at the table and analyze where the groups have either stayed the same and like moved cluster ID, split apart, and what differences do you see with the groups going from like 3 clusters to 4 clusters to 5 clusters. Is this making more sense, Mohammed, right here? How's this looking on this question right here? Looking at the code, now, obviously, I didn't do exactly what you needed to do, but this is the idea of the code right here, creating your clusters, make sure your data has been cleaned and organized, and you should be seeing answers that should be seeing clusters split and break apart going from 3 to 4. And then you want to ask yourself, is it giving us information right here? You can see the way this data was run. With this 4 clustering scheme, these people spend a lot on households. These people don't. We probably need z-scores. And then right here, you see these people are buying a lot of meat. These people are not. So the z-scores is going to make it easier. What is the code to check the centers? Just running cluster K5 centers. The K5, if you have the clustering scheme and run the centers of it, we'll look at the centers of each cluster right here. So this is going to look at where the center, which is the mean of the data. And then I've got a video playlist on that that's going to be really helpful. And we can, Olivia, we'll circle back to it. We got a lot of time today, so we'll do that. But that will check the cluster centers right there. So tell me if you have any issues with this. This is the majority of the code. I have a negative y-intercept. Oh, that's all right. And then it might be illogical. So Olivia, you're on track, it sounds like. Your y-intercept might be illogical. Just make sure you use our interpretations that we have, and we'll circle back. We'll be doing that here in a little bit. You got it, Olivia. That's a great question, because it is coming up. Yeah, I think we should do that. We'll do that here. We got the next question. Question 2 for 320. Let's go check out some question 2 for 320. Thank you, everybody. Let's do it. Question 2 for 320. My goal, especially for these upper level classes, is to kind of like put people on track, have people kind of ready to go. And let's see out here. Sunday. Linear regression part 1. Question 2. If I'm mistaken, in question 9, it asks about the median instead of the mean. Aggregate. Aggregate y tilde or tilde dot tilde. I'm going to type in the chat real quick. Aggregate. And then dot tilde K4, whatever you're using. Data equals data frame. Fun equals median. I think that should be correct. Very similar to that. Check the code. But it's dot tilde, and that's all your y's. Tilde, how your clustering scheme. Your data equals your data frame you're using. And then the fun equals median. And that will get you the median right there. That'll analyze the median. So check out that code right there in the chat. Good question. And the question was for question 2, AB line. Let's go check out some AB line for question number 2. I might need to look at the book question. There's a lot of parts to this. Matthew, if you're still here, you might be trying to add a line. So let's talk about adding lines to data. And let's go check this out, because there's not a question 2. So I got the code, but it asked the mean of question 7 and it asked the median. I'm not sure if it's supposed to have this be the same or not. The median will be different. The median will be different. The median will be different. Let's check out BS320, adding lines to data. Here we go. So with this right here, we're going to load up the data. I have the code for the first part. I just want to add the line. Which question? Can you copy the question? Data ex3 NFL. I don't have reg class loaded up. So we need to go here to library reg class, load reg class. And then when we type data ex3 NFL, it will load in. So you have to have reg class loaded in. Which one are you working on? You're trying to create a regression line, right? EB line. Which question? Like question 2. Is this line of the code that fits them all right here? Is it this one? Like, so I wouldn't use AV line. It's one way to do it. Line of code that fits the model. I think this one right here, right? So we first have to create a regression model, which is what we're doing in 201 right now. So tell me if this is what you're doing right here. This one right here is C1. So in this one right here, we have to create a regression model. So we're going to go ahead and create a regression model. I'm going to create it from a little bit different of data. So I'm not using your data, but watch this right here. Data, survey 10. This is not your data. Let me put a note right here. Brian is using different data. So I'm using different data right here. Fit this simple. Am I not doing the right? Is this? I'm on assignment 5. Are you doing it? Are you doing the assignment or the activity? Is it the assignment or the activity? Is it the assignment or the activity, Matthew? Good questions, Matthew. Is it the assignment or the activity? And I'll show how to do that right there. It might be the activity. Activity. Oh, cool. Yeah, that's where I was confused. Okay, so I'm going to show it on the assignment, and then it'll show for the activity too. So the first thing you need is a model. So how do we create our model right here? How do we create, what function do I create to write a linear model? So how would I create a linear model? So this will help out right here. Oh, no worries, Matthew. I was like, there was a disconnect. I was like, I don't see it. how do I make a linear model? Linear model. I'm giving hints. How do I make a linear model? What code do I start writing to write a linear model? LM, you got it, Matthew. Excellent work. Matthew, you're doing great, man. We write LM to make a linear model. What is this doing right here? Why do I do that arrow right there? What's the point of the left arrow? Like, what is the point of that? Why are we doing that? And I'll explain. You might be writing it. We store into things. We're going to store this linear model into an object. And we were actually just doing this moments ago with the clustering scheme right here, where we were storing the clustering scheme into the same thing. So exactly, Matthew. So what we're doing right here is a very similar thing. We're making the k-means algorithm from the Kroger data. We're telling it the centers, other arguments, and then we're storing it into the object k3, and then we're appending that onto data frames and stuff right there. So we're going to use the LM and store it into the object M. That's just a place to store it. We could call it model 1, whatever you want to call it. The name doesn't matter. We just use M for a very short thing to type, so M makes sense for model. Now we're going to go right here. This is just my example. I'm going to do height tilde weight, comma, data equals survey 10. This is an example, but we use y tilde x, comma, data equals data frame, because the variables I am using right here are inside of a data frame. If they're inside of a data frame here, you have to do y tilde x, comma, data frame equal, or data equals. And you can see right here, here's the height vector, the weight vector, and it's inside of the data set survey 10 right there. So when I create this right here, it'll create a list. Now, a list is basically a folder of things. So if I want to make my model, here's the easiest way to make it, and we should accept this. Visualize model M. This is the code that Dr. Petrie wrote to visualize your model. You do need a little bit of space right here, and this will visualize the model. There is our linear model right here, visualizing the relationship we have predicting somebody's height from somebody's weight. 201 is doing this right now. So the way it wants you to do it, though, is to do the following. We want to go here to plot, and let's go here to height, and we're just going to literally grab this, y tilde x, comma, data equals. You notice we get this plot right here, and then we're going to go and add something to this. We're going to go AB line, and we're going to go M, we have to have our model, and we're going to say col equals red. And now we get the red line. So now we have added a red line to this. But now we're going to go here and add another line. That's what AB line does. And we need to put in a second argument over here and go to y equals the mean. And we're going to go the mean of the y variable. I hate that it's starting to crowd the screen like this. I want it all to look like this. We're going to add a second line for the mean of survey 10, $ height. And then we're going to have a second argument right here, col equals blue. And it doesn't like it. It says no. Oh, is it H equals horizontal? It's H. Oh, what's wrong with my color? Col equals doesn't like the color. Really? Green. Why is the color not changing colors? Oh, wait. Oh, I have it inside the mean. Have my argument in the wrong spot. There we go. And so this right here is showing the naive model, and this is showing our model. And our model is doing a lot better than naive. This is a big concept for 320 right here. And does this make sense, Matthew? What I've written right here, I'll drop the code in the chat for you so you can kind of use it, manipulate it. And as long as you have, that's the longer version right there. We can do that coming up here, Brianna. You bet. We haven't done it yet. We're going to do some more 201 coming up. Got lots of 201 questions ready to go. 201 questions. I need to make that screen where I show what's coming up next. But is this making sense right here as you go through the different components? I did a plot. You could use any color. Use blue. There's a lot of different plotting options. You can do like a line width. These are all just like preferences. You can change the line width. So you can go right here to make it like stronger lines. Line width equals 2. And now it's a little bit bigger right there. A little easier to see the differences right there. Price, either the colors are all fine. Yeah, it's just the color. It's just your choice of colors, and it's different things to do. And then you'd just be changing the mean of your Y variable would change. Does that make sense right there? You'd use tip, bright, price, and bids, and then the data frame you're accessing, and then you'll just use the mean of the Y variable. Does that all make sense, Matthew? You're doing an excellent job. That's great. Great work, working ahead and seeing how we make this regression model right here. And 201 saw this output today, or they'll see it later, when we do a summary of our regression model. And how would you interpret? How would you interpret this for tool 1 only? How would you interpret the intercept? Well, it works for both classes. When somebody's weight is equal to 0, we expect their height to be 56.34 inches. But 320, and let's put a note right here, 201 interpretation. Slope interpretation for 320. So we'll write 201 right here. A little easier, so it's right there. I do want to point this out. In 320, you would lose points for this, doing the 201. In 320, we say 2 individuals who differ in X by 1 unit are expected to differ in Y by B 1 units, where are 2 observations, because it might not be people. That where the higher X is expected to have a higher / lower Y. So please note this 320 right here. We would say 2 individuals who differ in their weight by 1 pound. Awesome. 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the individual who weighs more is expected to be taller. So once again, the interpretation of this output right here for the slope interpretation would be 2 individuals who differ in their weight by 1 pound, that's the X variable, are expected to differ in their height, because we're predicting height right here, remember, by 0.07 inches, where the individual who weighs more is expected to be taller. So excellent work right there. That's some interpretation. And then the R squared. R squared is the same thing for 320 also, where we say, where's my R squared? 36.13% of the variation in somebody's height is explained by the variation in their weight. Canvas content. You know, let's do a version of the Canvas content here. So it's time, everyone, for everyone's favorite thing. Time for some Canvas content. Let's hop over to the main screen and do some Canvas content. Let's do this. Stat 201 Canvas content coming up right here. Let's check this out. Okay. Stat 201 Canvas content. Ooh, it's coming up shortly. We got Canvas content due Wednesday night. Chapter 7 and 8. We'll finish Chapter 8 on Wednesday. You say, how? Not that long of a chapter. It's a very short chapter. Pretty much review. Okay, let's take a look at Canvas content number 8. Here we go, Chapter 7 and 8. Canvas content 201. If the residual and the observed is 16 points, if the residual is 1.1 and the observed is 16.6, what is the predicted value? So does anyone remember the formula for a residual? The formula for residual is, does anyone know here? The formula for residual? Residual formula is, who knows? I'll throw 100 points. Everyone knows the formula for residual. I'll write the way I don't like to write it. It is usually written as this. This is the formula people write for the residual. E is the residual. But what is the formula for the residual? Easy way to remember it. Boom, right there, Catherine. Great job. And Olivia, excellent work. Residual equals actual minus predicted. So the residual equals the actual minus the predicted. What are we talking about right here? Well, if you have a line of prediction, then this would be the actual point. And so we'll draw this in red right here. Really? Really? Why can't I erase that? Oh, there it goes. So this is the predicted right here. And this is also the predicted. And let's change this right here. Go to green for the residual. Just kind of highlighting to make this clear. We might need this later on. The E is the residual and the residual is this. So this is the residual. Really? The residual right here is definitely what? The residual of this point is definitely what? Like if this was over here at 15, like if you went over and traced, and this was down here at 10, well, now you can tell what the residual is. So think about how you would solve this residual right here. You would have to know this residual is what? This residual is going to be what right here? So think actual minus predicted. So what is the actual value of this point? What is the predicted value of this point? And what is the difference between the actual minus the predicted? Good review right here. This is the statistical notation. This is the way to remember it. Residual equals actual minus predicted. So what is the, great job, Catherine, right there. Good practice. It is 5. Great job, Brianna. So the residual here is 5. And so now let's take our numbers, plug them in. The residual is 1.1 and the observed. Now, the observed is the actual. That's saying you observe this. It is actually this. Unfortunately, you do have to know some synonymous words. So if you see observed, you see it says, what is the predicted? So we're only missing predicted. Observed means that's the actual value. So 1.1 and 16.6. And so we'd plug in some numbers right here. 1.1, 16.6. So what could we do right here? Well, I think we could just take and mathematically just plug to the other side right here. It looks to be about that, right? So what you could do is you could just solve. You'd have to subtract on the other side right here. You go 1.1 minus 16.6, and we get that, but it's a negative version of that, so it's positive, and then just plug in the value of 15.5. Double check by doing this. Does this equation work out? Are we good right here? Is this true right here? What do you think right here? Oh, yeah, we should be able to time. We'll be circling back. Mohammed, you bet. What do you think right here? Is this true right here? Is this solving out accurately? Is this solving out and working correctly right here? I'd say yes. We just found the predicted value. So we just found the predicted value of 15.5, and we're losing it. No, where'd it go? 15.5 is the predicted value of what we have right here. Consider the following jump output: finish time in minutes, age in years. So here we are, a positive relationship. 34.4% of the variation in finish time is explained by the variation in age. People who have an age of 0, that sounds illogical to me, are expected to have a finish time of 156 minutes. You have an age of 0, you won't finish the race. You don't exist. Or you're just born, you're not racing. I see a bit of plot thickening issue. What are our 4 conditions for regression? Good review. This is where we practice. We don't even know what the question is yet. But what are our 4 conditions for regression? And I want to point this out. This information right here is how your screenshot should look for visualization 5. If you're working on the visualization, this is what you need for the visualization. QQ, straight enough, no outliers. Plot doesn't, Olivia right there knows the conditions. And then plot doesn't thicken. Little bit of plot thickening right here in the residuals. So the residuals right here show some sort of plot thickening. And the residuals, is there an issue? Minor issues. And we see 2 individuals, or for each 1 unit increase in age, we expect somebody's finish time to increase by 2.43. So what's it ask? R squared. R squared is going to be R squared right there. That's easy. 34 point, there we go. That looks right. The other one doesn't do it correctly. Read it. 34.041% of the percent variation finish time is explained by the variation age. Slope interpretation. Slope is going to be this variable right here, 2.43. So, it just has us quote it. Well, that's not fun. Doesn't have an interpretation. I wish it had it. But we'd see right here, for each 1 unit increase in age, we expect somebody's finish time to increase by 2.44, rounding. And then the intercept is the B0, which is the first one. Y hat equals B0 plus B1x. Do remember this equation. Practice writing it down. We wrote it down earlier, and we have the interpretations. And there it is right there. Y hat equals B0 plus B1x. And please notice that this equation is right here. We are predicting someone's finish time. It's on the y-axis. That's y hat means this line is a prediction line. And then B0 is the intercept when x is equal to 0. B1 is the coefficient of the slope. And I do want to point this out. You will probably be interpreting these on the test, and make sure to do the right interpretations. So we just need to quote the slope, it looks like. And the slope is going to be, that's the slope. The intercept is 156. And that would be runners who have an age of 0 are expected to have a finish time of 156 minutes. Not logical. Find the predicted value of a regression where B0... So now we need to write this out. See if you can solve this. I'm gonna start writing this out slowly right here. We have B0, which is the y-intercept. And we have B1, which is the coefficient of the x. And then we have x. So if you know the equation, we're going to go right here. We're going to start writing it out. See if you can solve this. Try solving this while I work this. Let's see if you'll get it. 16, you might be right. I think you are. Yep. I think, Olivia, great work right there. Making sure you get it. So it's y hat equals B0 plus B1x. Remember, it's for each 1 unit increase in x. Right there, Josephine, another 20 points. Great work. So we want to find the predicted value, which is y hat. That's what we're interested in. And so we're going to say right here that is equal to 11 plus, And then we have b1 equals 1, and then the value of x equals 5, and that is equal to 16. Great work. That's the predicted, and that means we would predict whatever this is that y equals that. Adding together all the residuals will always sum to 0. True or false? It'll always sum to 0. Adding together all the residuals from a regression plot will always sum to 0. True or false? It's like I know what's on the test sometimes. That is 100% true. We call it the line of best fit for a reason. I don't have that graphic up anymore. Oh, no, wait, there. No, we don't have that graphic up from earlier today. But it's the line of best fit because when we do this right here, the line goes through the data. And so it's going to be a line of best fit. So some residuals are going to be positive, some are going to be negative, and the residuals will kind of counterbalance each other because it's a line of best fit. So that's what we mean when we say the line of best fit. For each 1 unit increase in x, we expect y to increase by b1 units on average. Which one do you think this is? Which one sounds like this? For each 1 unit increase, and they put on average. I need to tell my graders, I don't care about that on average. If you know the r squared value, to find the correlation, you do it to the following. Let's do one more version of this, and we'll do that real quick. This is the slope. Now, so this is where we should get 100. 100, 10 out of 10. Okay, let's preview it again. Let's do one more version. Let's see if it has Olivia's question. Jump output. This one's good right here. Oh, that's r squared. Let me see if I can get the one Olivia has. Preview. Try to do one more here to get. Am I going to still not get it? We'll try here, and we'll do the next question. Is it going to just keep showing this right here? Really? I know your question, Olivia, and we can... Here, let's just submit this quiz. 2. Oh, no! Let's preview it. Oh, man. Submit quiz. I'm trying to get your version right here. This is rigged. So whenever you find r squared will always be what, Olivia? R squared will always be what? R squared must be a what number? Yeah, here it is. R squared will always be a what number? Because you're squaring r. So r squared will always be a what number? R squared will always be a what number? R squared will always be a what number? R squared must always be a what number? R squared must always be a this number. R squared must will always be positive between 0 and 1. Great job right there, Muhammad. R squared will always be between 0 and 1 unless we're doing like R squared holdout. Interesting stuff for later. R squared will always be between 0 and 1. Stat 201. Stat 201. Always be between 0 and 1. But can you tell me the value? First off, just tell me the value of r squared right here. Tell me the value of r squared, and this will answer the question. Tell me the value of r squared right here. What is the value of r squared? Just be like, r squared means blank percent. I'll explain it. Blank percent of the variation in someone's weight. Oh, excuse me. Blank percent of the variation in someone's GPA, that's the y variable, is explained by the variation in their weight. Blank percent of the variation in somebody's, so it'd be what? And we've got our r squared interpretation down here. So 4.6%, then we times by 100, 4.6% of the variation in somebody's GPA is explained by the variation in their weight. But here's the thing. What is correlation? Take a moment right now and tell me correlation and tell me why it is this. This is a good question that is on the test. We don't do a lot on correlation on the next test, but r squared you can use to find correlation. And so this is where people make a mistake because what is the correlation right here? Take a moment, see if you can find the correlation and look what you have to do. And it'll answer the question. So this is where, because sometimes people just look at the answer and be like, oh, that's the answer to the question. But understand, like, okay, wait, if I do this to r squared, I should probably look at this. It's going to give you a hint. So what is the correlation here? If you have r squared, how could you get the correlation? Because r squared is percent of variation y explained by the variation x. So what could you do to this to get r from r squared? What could you do to this to get r from r squared? Exactly. So is this the correlation, yes or no? Be careful. Is that the correlation, yes or no? Why or why not? Look at it. Look at the graphic. So I square rooted it. I took r squared and square rooted it. Is that the correlation, yes or no? Do you see it? Carson, great job. Carson, 100 points. You are correct. Carson's saying it's negative. Exactly. It goes down, so it's negative correlation. So you could look at the slope of the line or the direction of the plot. Correlation would be negative. Because when you square root something, you get positive, negative. So you're like, well, how would I know which one it is? We can look at it. We can see the slope right there. So the answer to the question would be, take the square root and check the direction. Does that make sense? So that's what we did. We took the square root and then we checked the direction. So don't just take the square root of it, because if it's negative, you need to make sure to show its negative correlation. For each one unit increase, this is slope interpretation. This one again, R squared is going to be the R squared interpretation. Awesome. People getting those 100s. The slope is what, like the 21? Wait, no, it's 2.4. And you got it. I'm going to make a mistake right here. Brian's going to go too quickly and make a mistake on this. If a residual is positive, which is larger. So if a residual is positive, let's go look at this visually. This point right here has a positive residual. So which is larger? So help me out right here. The line is the predicteds. And that point, I'll show only that point. So which was larger, the actual or the predicted right there? So if the residual is positive, which means it's above the line, that's a point right there. The actual, Catherine, amazing work. Thank you everyone for still following along and hanging out. And so the actual is going to be larger because we're talking about residuals, so it's actuals and predicteds. If the correlation coefficient is this, what is R squared equal to? 0.5 times 0.5. 5 times 5 is 25. Move decimal over. If you're looking at what we're doing, we're just going 5 times 5 is 25. Submit quiz. Anyone else get another 100 and say, who's not afraid of these Canvas contents? Not me. Not me. So remember, these Canvas contents look a lot like the exam. They're just testing your general knowledge on things. So if you're able to ace these Canvas contents and come back to these videos, write these down, maybe put them on a little flashcard and be like, I'll just ace these Canvas contents. Don't be afraid of them and use your notes and try to draw the examples. My biggest fear is people just look at the answers to these and say, that's the answer, that's the answer, that's the answer. But try doing the concepts. Try checking your knowledge to be like, that's an actual, that's a predicted. The line gives predictions. The points that exist, the y values are the actuals. And this would be a prediction from the line itself. So that would be a y hat right there. So this is what it was predicted to be. And this is the value of its x right here. If that's the equation, so that'd be b0 plus b1x. Great stuff. I think it's time for another question. Let's do it. Next question that was Canvas content. Could we go over Canvas content? We did Canvas content. Can we go over some chapter 7 homework? You bet. And then Mohammed, your question is next, it looks like. So stay tuned. Next question. Thank you everyone who lines up the questions. Amazing work. So let's do some homework right here. If you have more questions, let me know. We probably have more time because we've got 50 minutes. I ended office hours a tiny bit early on Thursday. I had a headache. So it's rare that I end office hours early, but every once in a while I say I'm taking some time. It was a long week, busy week, but I really appreciate how much people use these videos. A lot of people, like, I can see the analytics on it, and sometimes, especially later in the semester, like 1,000 people are using 100,000. I wish. That'd be weird. I'd be like, why are 100,000 people using our videos? Like, makes no sense. Let me sit up straight. I think I break this chair by sitting so close to the edge of it. And let's get homework 7. Assignments are loading. Homework 7 loading up. And I want to say this. Amazing work to my class today. We had over 200 people live at one point. Attendance was actually almost as good as, or pretty much just on good as how much it normally is. Let's have that happen Wednesday. Probably speaking to a few people right now. But if you were in class today, here's 100 points to you. Thank you. Hashtag show up. That's what matters right there. Okay, let's take a look at some My Pearson homework 7. Let's go take a look at this. So I'm going to shift the dates around these a little bit, but this is homework 7 right here. For many people, breakfast cereals are an important source of fiber in their diets. Eat more fruits and stuff. Certain blah, blah, blah. We're making an equation. Here's an equation. The predicted potassium, that's what the hat means on this. That means predicted. Whatever the hat is on means predicted. Usually we write the equation as y hat. So if you see right here, y hat, that means the predicted y. B0 is the y-intercept. Let's highlight some stuff right here so people can see what we're talking about. This equation right here is y hat is the predicted values. That means predicted. B0 is the y-intercept right here. Oh, Olivia's crushing it. Love it. And then B1 right here is the slope. So it's important we can break down the important parts of this equation. And then the x variable is just the name of the x variable. So we can kind of see what's going on right here, that this is when x is equal to 0. This is for 1 unit increase in x. And y hat right here is the predicted value, which is the line itself. So when we do this, we're just going to plug in and make predictions using that line. Olivia, excellent work right there. Another 50 points. We're just going to take and plug in the number 8 to make a prediction of how much potassium it would have. And that is a prediction. We're not saying it will have this. We're saying I would expect if something has 8 grams of fiber, we multiply by 26, and then we add 37. All we're doing is just plugging in 8 right there. And there we go. Olivia, excellent work. Great job. That is a prediction from the line itself. Great job. Here we are with the next question. The next question is very similar, using a similar equation. Oh, Connor, excellent to see you, man. Thank you so much for all the time series stuff. Excellent work on that. We're doing some cool stuff with stocks right now, and your time series stuff is really awesome. I need to up my game. Always trying my game. Doing some regression right now for 201. Connor was one of our TAs for 201, so he knows these questions probably well. Predicted potassium is equal to this equation again. From your model, you can estimate a certain content, What does it mean if it has a negative residual? Oh, this right here is chapter 7 homework. What does it mean if something has a negative residual? If something has a negative residual, where would it be? So if something has a negative residual, so if we have here a line of prediction and something has a negative residual, I want you to think, here's the line of prediction. This is y hat. And then we have an actual point down here. That's the value of y. And thus the residual is this right here. That's the residual on one of the stairs. So where would this be right here? They're gone? Oh, you're saying, yeah, I see it. Connor was pointing out the stair right here. Connor is right about that. Those stairs right there for showing the slope. Connor's right. It would be, and the stairs were where? So we call this the line of prediction. That's the prediction line, the line of best fit, the regression model, the predictions we're making. So I'm going to say I predict y to be this, which is y hat. So if something has a negative residual, which this is the negative residual zone, this is the positive residual zone, and anything on the line would have a residual of 0. So a residual just tells us how much we miss by. So anything with a negative residual would actually be where this is the actual, and it would be where to the predicted. Anytime something has a negative residual, here's the prediction line. The actual point, the actual observation. What do we mean by actual? This would be like the actual fat, excuse me. So if we have here fat, this would be the actual fat of a burger item. And then this would be how much fat we predict it to have. So this would be its predicted fat up there. Like we predict it's going to have way more fat than it actually has. So the actual would be where to the predicted. So if it has a negative residual, the actual, the potassium content, which is what we're predicting, is actually lower than the model predicts for the cereal. Does that make sense? If you look at this visually, this is the prediction, and the actual value of it is lower, thus the residual is negative. Anything below the line has an actual that is lower than the predicted. Because the formula for residual is going to be residual equals actual value of y minus predicted. Also, I like to write it residual wrap, residual equals actual minus predicted. So the actual is going to be less than the predicted. Just plug in some numbers right here, like 10 minus 15, and this would equal what? Who knows? 100 points on the line right here. 10 minus 15. Like if I were to tell you that this is 15 right here, and I were to tell you that this is 10, what would the residual be? So what would the residual of this point be now? If, and we'll make it very clear, we're only focusing on that. What would the residual of that point be? Oh. What would the residual of this point be? So what would the residual of this point be that was predicted to have 15 grams of fat, actually had 10 grams of fat, what would the residual of this point be? So it was predicted to have 15 grams of fat. That's where the line is. And it actually has 10 grams of fat. What would the residual be? I'll pause here for a moment, take a moment to see if you can solve it. And be like, oh, because it's actual. We'll highlight its actual. There's its actual. We'll highlight its predicted. Thus, its residual is what? Its residual is going to be what? Who knows? 100 points on the line right here. Who knows what the residual of this? All you're saying is like, how far is it above or below the line? So that point is how much away from the line in terms of positive or negative. Connor right there earning everyone 100 points. Thank you, Connor. It is -5 right there. -5. Connor wants those points right there. You bet. So -5. It's 5 below the line. Connor, you might have a lot of points. Check your level, Connor. Check out. I'm leading the way right here. I think I've got Galaxy tier, Brian. But check out your points right there. See what level you're at. Swinging by. Appreciate it, Connor. And so the potassium content is actually lower than the model predicts. There we go right there. Fantastic. And it probably gives an explanation. Now, when we go to R squared, kind of already there right there at 0.3 extra credit, Kylie right there, almost at the 1 point level. And then the bonus is when you go to, you have to get 50,000 points, but I'm way beyond. The correlation between a cereal's fiber and potassium content is 0.919. So that's this correlation. What fraction of variability in potassium is accounted for by the X variable? Only gold tier. So when we go right here, we've got our interpretations on the screen, and R squared is the percent of variation Y explained by the variation in X. So all we do is we take the correlation and we square the correlation. Now be very careful. R squared is not the same thing as correlation. R tells us the strength, direction, form, and is impacted by outliers, where correlation does that, where R squared is a fraction of variability or percent of variation Y explained by the variation in X. Be very careful. This is not correlation right here. It is R squared though. So all we're going to do is just take this and take 0.19919 and square it, just to make sure I'm doing this correctly. Caret goes on the X. Price, I believe... Yes, that sounds correct. It seems like we should predict price. I believe so. That sounds accurate. I got to make sure I run this properly. That sounds accurate. Yep, Casey, excellent work, because caret's going to explain price. Great job, Casey, right there. So 50 points working ahead, or 20 points, 50 points. And we got that right there. I was afraid I was going to make a mistake. Okay, here we are with residual plots. A residual plot, which this is a lot like your assignment now. A residual plot is going to show you all of the residuals. So Casey, this goes to the visualization. Make sure to add this on by going to the red arrow right here and clicking plot residuals once you make your line. And you can get a residual plot down here showing you how your residuals look. You'll add this on and you'll want to see, do the residuals have any sort of pattern, especially like a plot thickening. So this looks not amazing. It's got weirdness down here a little bit, not horrible, but I mean, our regression's only 2%, so we don't expect much. You can also see what it kind of looks like there. So you want your residual plot to look like nothing at all. Nothing at all. What do you notice is the problem with residual plot A? QQ straight enough, no outliers, plot doesn't thicken. What is the problem with this residual plot right here? Yes, Casey, great work. I thought it might help out to see where that's at, the plot residuals, and make sure that graphic's on there. So if you got that graphic, you should be good. What issue do you see with this one right here? QQ straight enough, no outliers, plot doesn't thicken. Yeah, we're going to do it. I think that's next on the line. You bet, Ali. Abby right there, Ali. I can't remember. You got it. We're doing question 3, I think. Mohammed wanted question 3. We did, in the stars, we did question number 8, I believe. What looks to be the issue with that first plot, plot A, QQ straight enough, no outliers, plot doesn't thicken? What looks to be the issue with that? So remember, the conditions for regression are QQ straight enough, no outliers, plot doesn't thicken. We'll show them on the screen right here again so we can make sure we know them. QQ straight enough, no outliers, plot doesn't thicken. There's all the conditions right there. And what looks to be an issue with that one right there? Looks to me like QQ, it has to be 2 quantitative variables if it's a scatter plot. Straight enough looks to be good. And no outliers. That does have outliers. So this definitely is an outlier right here. And the residual plot. Wait, what? There's plot. Okay, except for a single point. There we go. I was like, where's the outlier thing? Next one, QQ straight enough. Not straight enough. So this one right here has a curved pattern, which is not straight enough. And then this one right here is a fan pattern, which is a plot thickening issue. So the next one is going to have a plot thickening issue. So the fan pattern tells us that the model's predicted power is actually getting stronger. The predicted power of the model increases because it's getting tighter around the line. The line would be here at the center of the model going through the middle of the points. Now, this is probably one of my favorite questions for looking at residual plots. We'll look at it real quick here again. And actually, I did this one. I might come back to this one later on. This one is in last week's video, and I go through it. We can circle back to it in a little bit here. But this one is a much longer solve. This one is a very good theory question right here. Let's see if it gives a different version. I want to point this out right here. What do we want to see in a residual plot? What do we want to see in a residual plot? Remember I said earlier? In a residual plot, we don't want to see anything. Residual plots show us the leftover variation, and we don't want leftover variation because it means we've left something that we didn't explain. We want to see randomness. Which of these plots show randomness? A, B, or C? Which of these plots look pretty random? A, B, or C? And this is a residual plot. We want to see randomness in a residual plot. So which of these plots show randomness? A, B, or C? A shows a violation of the straight enough condition. We wouldn't fit a straight line through that data. C shows a thickening of points. So C has a problem with the plot doesn't thicken. So which of these plots show randomness, which is what you want to see in your residual plots? You want to see just random points. So which of these show randomness, A, B, or C? Which of these would show good randomness? And this is where people just are like, wait, what? That's good? That's good. I think that's where the confusion lies. The good plot here, the one that we like, is plot, 100 points on the line right here. Who's got it? The good plot right here, the plot that shows randomness, that means our residuals look good. Like we want our residuals to just be random. Like we don't want any pattern. We don't want any leftover variation. That's what residuals are. They're leftover, like a residual effect. We don't want anything left over. And the one that shows good randomness is B. This one indicates that the model is appropriate, meaning like it's a good thing. We've done a good job right here. And I think that's one of the most confusing things when people look at this and they say, wait, that's good? So yes, that's very good. Now, I do want to mention, since we only have 36 more minutes, I did this one in last week's video. I did a long solve of it, did each problem as we went through. This one is a little bit longer, one of the toughest ones on here, and use the regression solver. I've got a regression solver. I'll show where it's at, but you should have it. I think all classes have access to this. So look for last video, and it should be there for the SAT question marked. It's a bit of a solve. It takes some time. And if you go to the modules, you will see, because I'm going to do some 474 here in a second, you will see the regression solver right here, and use the regression solver. It'll solve the equations for you, and you can get the slope, the intercept, and make predictions. It's a really good problem. It's a pretty tough one. It's going to be definitely one where people lose points probably. The other one's a little bit easier and more conceptual. This one's very applied, which is good. With that, we're going to head over to 474. Let's check it out. 474, which one, Muhammad and... Was it? I think Gabby, right? Take your pick. I think Muhammad was saying 3 or 4A. Which ones? Which question do we do? We're going to use we're going to go 15 minutes here on 474, and then I'll look through and see what other questions there were. And then we do visualization to end. We'll do visualization to end. So we got 15 minutes on 474. What shall we do? Take your pick, 474. Getting it up in the background right here. Try to hop around classes and assignments. 4B, let's check out 4B for 474. Here we go, 4B for 474. Let's check it out. Question 4B for BAS 474 is going to be, here we go. Kroger is interested in using the cluster identities to aid in identifying segments where customers' offers could be designed, people who cook, people who do this. While the clustering scheme you found is valid technically, algorithmic point of view, the end result is not very interesting and definitely not useful for Kroger. Determine how the cluster differs from each other, then explain why Kroger would not find this clustering scheme useful. So this is really good right here, and I can't go. So we might have to pick a new one after this because I don't want to show the answer, and I want people to think through it. When you get your clusters, which do we have clusters still? You want to look at your clusters, and what you really want is z-scores. So we don't have z-scores. Do I have the scale data function? Mine are going to be different than yours. I'm trying to think of a data set I could use. Let me do this. Data. Body fat. Okay, there we go, the body fat data. And I'm not going to transform these. It takes a little longer to go through. Okay, good. These are all quantitative right here. We want to look at groups of individuals right here. So what I'm going to do is I'm going to go to scale data frame, body fat, and I'm kind of going through body fat scaled. Okay. So that's scaling it right there. That's just a graphics warning. We're good. I hate that it does that, but it does it all the time. So we have scaled body fat right now. So now everything in here is z-scores. So now we're going to run the k-means algorithm on this, and we're going to do k3. And let's see right here. Does this come out with something meaningful is the question. Can we get meaningful clusters out of this? So I'm going to go to body fat. I didn't transform this. Brian did not transform his data to achieve normality. Bad. Okay. Just going quicker. It'll take more time to transform each variable than it would to go through here and look at the z-scores. We're going to go through here, do the end start, number of times the algorithm restarts to find the centroids, and we'll do 20 restarts. Iter max is the max amount of iterations till it reaches convergence, where it tries during an iteration. So it'll go through, try to find cluster centers. It'll do the best it can at reassigning group centers and moving the centers each time to the new group centers after it reassigns, then moving them and reassigning, moving, reassigning. Those are the iterations. And then once it either reaches max iters or it can't do anything, which is called convergence, it'll restart the algorithm again. This is because it finds the best answers via... Statisticians love randomness. So it's trying to find the best cluster centers, but it doesn't know where to put the centers. It just randomly drops them down and starts assigning. You should use set seeds. Use set seeds to replicate. So use set seeds to replicate. And it'll definitely instruct when to use set seeds. So I would throw in here like a set seed on this and just do something like 474. Make sure to use your set seeds to replicate. And the iter max, we'll just go 30 iter max. And what's it mad about? Centers. Oh, did I not tell it the centers? It's mad at me. I didn't tell it the centers. There we go. Let's run the chunk. Running the chunk will run the seed in the chunk. And let's go ahead and take a look at this right here. Okay. Got a lot going on the screen right here. I'm actually going to take this and store it as a data frame for a moment and evaluate the data frame. Looking at this right here, do I see anything that really jumps out? These people in cluster 1 are all below average. Does that make sense, Mohammed, what I'm looking at right here? All of cluster 1 has a z-score of like -1. And then all of cluster 2 has z-scores of zeros. Wow, almost exactly 0. And all of cluster 3 has z-scores that are basically positive. There's no distinct... Oh, that's interesting. Everyone's age is very, very similar. There's not a lot of variation in age. Let me look at that. It's probably just that variable doesn't have a lot of variation in it. Oh, wow. That's about the most interesting thing that's not interesting, is that age doesn't really create the clusters. So we're not... Oh, good to see you here, Ditto, right there. So we're really seeing not much difference in the age. The weight, once again, these are my below average people. These are my average people. There's no difference between ages between anybody, really. They're all towards the middle age if you average out the clusters. And these are my above average people. So it's like smaller people, medium people, bigger people. I'm going to go to here to 5 clusters. And let's see if we see anything interesting here at 5 clusters. And let's go look at the data again. Okay. I'm trying to see if anything... Oh my gosh! Mohammed pointed out. Now that's the kind of stuff you want to see right there. That's the kind of stuff you want to see. Holy mackerel. Well, age is still not doing it. But we're seeing, not just that breaks the trend. If we're trying to market things to people, we want things that jump out. We want, that's it. And there's other things too here. But look, like the height's not that different. These people are very distinct on a few key characteristics from multiple. Really, that's a characteristic. Like if these were items, we could market those. I'm trying to see if any of the other clusters have. Let me go with like a 7 cluster scheme. Then I might get something very interesting. I'm looking for interesting things where like one particular thing jumps out. All right, let's see. Looking at these are all Z-scores, so it just tells us how unusual it is. And these people are very unusual. These people weigh a lot. These people are pretty high in this. They're high in hip measurements. Interesting. This is our big cluster again. It's not really making very distinct. Well, these people are high in hip, thigh, and knee. Actually, that is interesting. You know what? Here's the thing. Think about this, and we might have done something here. So this is where maybe we get into something interesting, but we still don't have like one key characteristic that jumps out. But do you notice how these people right here have higher body fat? Like they're higher in body fat. They're actually the second most above average because these are averages. Like they're the second highest body fat group compared to this group. And then what do you notice about these people's weight, their neck measurements, their chest measurements? When you get down to hip, thighs, and knee, all this right here, or their ankles and their biceps and all these other things, their forearms and their biceps have average measurements. These are probably people who carry their weight in their what? I mean, it makes sense. They have higher body fat. And then you look at their hip measurements, their thigh measurements, their knee measurements. These are people who carry their weight more in their lower body. But then you go up to here, and you've got the heaviest of people, and their weight is off the charts. Their height is not. Oh, I didn't notice that. Wow, this group, and I think that makes sense. Maybe there's something going on right here where there's more females we know are generally shorter than males on average, but that should have jumped out to me immediately, and that is something interesting right there. That is very interesting. That is ridiculously interesting. Does that make sense, Mohammed, right there? When I see that for group 6, I'm like, that was a showstopper right there. That's like, wait. A lot of these Z-scores right here are very next to each other. Like, yeah, I mean, these are above average, but that is a ridiculous setting itself apart. These are very short individuals. They are 11 standard deviations away from the mean. That is, it might just be like one person. Let's go check out the size of these clusters. I call it K7. And let's go here to clusters. Is it one person? It's one person. It's a very unusual one person, though. I mean, not in a bad way, but in terms of Z-scores, they're very unusual. It's one person, though. Also, cluster 3 is one person. So it's clustered off the most unusual people away from everyone else. So, exactly, this is a shorter person who is storing their fat more in their lower body. And they're way shorter than everyone else. We could find them pretty easily right here. By going to the body fat data set and just finding the shortest person. That might be a data. It might be a data misentry. It might be a data misentry. You do not know these things. I think it's a data misentry because that's 2'6". That's 2.5 feet tall. I don't know if how tall is shortest person ever. What you gotta do? Shortest person alive is how tall? Oh, there's people who are 2 feet. So maybe it's possible. It's possible, but it's one of those things that makes you question whether does that make sense with the data. We've gone back to data validation now. Like we've gone back to should we include this? Should we not? I mean, they are clustered off into their own cluster. And when you think about what makes this person the most unusual, they're most unusual by their height. You can just see the Z-score right there. pretty obvious right there that they're an unusual doesn't mean bad. Once again, it just means far away from the group centers, as is the person right here who has the highest measurements. The tallest individual is also going to be our individual in the one cluster by themselves. So this is the tallest. Oh, really? Yeah, so they carry their weight differently. So this person is very unusual. They're very above average in height. Is that correct? The height? Oh no, they weigh the most. So the highest weight, 363. They're pretty unusual right there. And they have some interesting combinations of weight. But what we really want to see with clustering schemes is things that jump out like this. Like, unfortunately, these cluster groups are very small, so it's not going to be good for marketing. I don't know how useful this would be. We're not really seeing that our clusters of greater than size 1 have distinct things in them. We're just doing marketing to individuals right now. So we really want to see a cluster having distinct characteristics that we would want jumping out. So just think about how, like, you'd want something. One concerned other question mostly is there a lot of other approach and make conclusions. Well, yeah, no, there's something to notice. I don't want to say the answer, but just be thinking if you want to market certain products, you want certain things to jump out and do certain things jump out. It's the best hint I can give right there. Was there another? I might have time to talk about a little bit more on something else. Was there another one you want me to talk about? I can't say the answer, but think about how if you're marketing and you want to market certain things, how should the clustering scheme look? And then think about, does it look that way? If you're interested in marketing certain products, certain people, certain Z-scores should be, more extreme, and you should see like a characteristic pop out. It's about as best without saying it we could do right here. Think about how that looks right there. Got just in time. We'll do another 4 or 5 minutes on this right here, and then we'll hop over to the visualization. Visualization. I got all these fake AT&T messages. We'll put up a break. Which other one were you wondering about, Mohammed? Which other one were you thinking about? Feel free to say, like, also discuss this one a little bit. I don't want to quite say answers, but I want to kind of allude and talk about how to view the clustering schemes and what we're kind of analyzing by saying, do characteristics jump out to us? Does this give us any actionable insight? So 3, please. Let's look at 3. Looking at number 3 right here. Let's go ahead and take a look at an elbow plot. So number 3 with the elbow plot right here, we are running through, produce the elbow plot, exploring the values of K from 1 to 20, tracking the iter max. Once again, Brian has different data. So if we're going to do this, we want to go through here and don't write your for loop first. That's a bad way to do it. Oh, no worries. Thank you, Mohammed. Excellent job right there. I appreciate it. 100 points right there. Thank you so much. It's, want to help out, but I don't want to give away answers. So go to k-means. And let's go right here to the k-means algorithm. We're going to take our body fat scale data. Once again, I'm doing different data and different things. It's got arguments we want it to use. So we're just going to copy these. Then we're going to fix it so we don't have that. And maybe I should have just wrote it. That looks correct. And then here's the tricky part. Is we want the centers to be equal to starting out with 1. Does that work? Could not find k-means because it's k-means not capitalized. Auto-completes your best friend. Could not, oh, that's my object k-means. It keeps auto-completing to my object k-means. It's very hard to tell the capital letter difference, but it's a capital K right there, and that's the problem. So now with the lowercase k, there we go, we got it. So what we want to do is we want to rerun this algorithm multiple times, and when we run the algorithm, we want to run it with 1 cluster. Then we want to run it with 2 clusters, and just keep going through here and keep iterating until we do up to 20 clusters. And the way to do this is with a for loop, and we just built our, it's coming right here. We're going to see, it's the skeleton right there. So we got the skeleton for the for loop built, and now we can take this and we can see what we need. We're going to right here and put the for loop and go with the skeleton, drop it in there with our control paste. And we have our variable is I, which is the placeholder, and 1 through 20. Now, what we want to get out of this, you bet some Skelly right there. We want to get out of the k-mean algorithm the total within sums of squares, right? Total. What's the difference between these again? Just want to double check. All right, then we look at the clusters. So we do want this one. Oh, is that the sums of squares naive right there? I think that's the sums of squares naive right there. The first one is the naive. And a good way to check that is if we had the remaining. I think that's the naive, because that's the total within sums of squares for the cluster. Because we want within the clusters. We want the total within, or the within sums of squares. Yeah, total sums of squares, and this is within the clusters. Good. Makes sense. The first one is for the naive, which is a throwback to 320. We just mentioned that concept last class. It's from the mean of the y. Good stuff for 320. So we have the total within cluster sums of squares right here. That's not what we want. We don't want the individuals. We want the total. There we go. It's just the sum of that vector, because there's 4 clusters right now. And then we can take right here and take this object and store it right here to within cluster sums of squares. And then we have to store it into position I. Probably should have written that outside the for loop, but I've done this enough times to make sure it works. And now we go here to within cluster sum of squares, store the object open vector. And now we have created a within cluster sums of squares. Now what we would like to see is a good review, and this is why I want to do this one. And it's too mad at me. We'll calm down right there. So what we want to see is we want to see a good elbow plot. A good elbow plot looks like this. You can see the elbow. This is like a perfect elbow plot. It'd be amazing. We never get elbow plots like this. The worse an elbow plot looks, the worse it is to see the elbow. And say it with me, if you know it. Good elbow, bad elbow, impossible elbow. Good elbows are, oh my gosh, I reversed it. Bad elbow, good elbow, impossible elbow. A bad elbow is one where you don't see the elbow and the sums of squares just kind of drifts downward. No. A good elbow is one where the elbow is clear and sharp and easy to see. So the elbow will come down, it'll drift down. We're talking about the sums of squares down here on the bottom. That's what we're seeing is and then bad, good, impossible. Exactly. Now, what cannot happen as we increase? Why is this elbow impossible right here, Mohammed? Why is an elbow like this that goes down then up impossible? Why would that be an impossible elbow? Why do we say this is bad because you don't see the elbow, good because there's a sharp elbow, and why is this impossible? Because as we increase the number of clusters, what would not happen to the within sums of squares? As we put more centers for the clusters to be the points to be closer to, what would not happen? It can't go up. Exactly. We wouldn't have points further away from cluster centers if we're increasing it. Imagine this. You complain that there's not enough gas stations in your town, so they add 50 more gas stations. Would it be possible to be someone to say, I'm further away from gas stations now? No, people would be closer. So as you keep adding cluster centers, the points will have less distance away from the cluster centers. And that's the within cluster sums of squares over there. As we increase the number of cluster centers, the distance points are away would decrease. Now, our goal is to find the optimum number of cluster centers. So we want to see an optimum, and this would indicate no optimum. This indicates an optimum, and this is just impossible for points to get further away as we add more cluster centers. So here's the plot right here. And then we would say, does it have a good... Yeah, it's like, yeah, if we put more gas stations in your town, because well, now I'm further away from them. No, everyone would have to be closer. The distance people are, the sum of the squared distance people are away. Exactly. Well, thank you so much, Mohammed, right there. 100 points. And I hope that helps explain, and this is kind of the code. I kind of did this one a little bit right here. Let's hop over. We're going to do 201. Excellent work right there. Some 20 minutes on this. We're going to jump over and do some 201 right here. Let's check it out. Some relaxing music right here as we do this. 201, visualization number 5. We might not have time for the whole thing, but let's check out 201, visualization number 5. Now, I want to point something out. We have a visualization playlist. So the visualization playlist, my gosh, my hair got long. The visualization playlist is a great place to go to get the visualization assignments done. Sometimes there's small changes to them, so make sure to read your assignment. So we're going to drop this in the chat right here. You're welcome, Mohammed. Excellent work. Visualization playlist. Dropping this in the chat. Going crazy with that chat right there. And let's go check this out. I'm going to bring up the assignment right here. It is spammed in the chat. And we go right here. Check up the music a little bit. Good chill music. I did Canvas content. We don't want to do Canvas content. We already did Canvas content. Visualization number 5. Let's go! Mario. Probably worst Mario impression ever. Maybe better than Chris Pratt. Who knows? You're welcome, Kirsten. Anytime. Using the diamonds data set, and I'm probably not going to do the diamonds data set right here. You're going to take 400 plus the last 2 of your UTID. Let's show how to take a random sample right here. To take a random sample inside of Jump, which is in the visualization playlist, you want to be inside of your data. So we're inside of the data. And then go to tables and go to subset. Make sure you take your random sample. You'll go here to subset, and then you'll click here. You'll enter in 4, then the last 2 of your UTID. If that's the last 2 of your UTID, great. Hit enter, enter. Make sure on the bottom you see 4 plus the last 2 of your UTID. So I'm going to use this data set right here for the assignment. Going through next, we see submit a Word document with the following visualization and associated write-ups. Be sure to include your name at the top of the document. Important stuff right there. Let's go ahead and do that in a Word document. We're going to put right here and say Brian Stevens. There we go. Might be a point. It is a point. So now we've got our name at the top of the document. Create a visualization using analyze fit y by x, where caret is the predictor and price is the response. Now, I don't love these wordings. If you look right here, caret is the predictor. We might not have enough time, Ashling. We can definitely do it tomorrow. We'll probably be finishing off this because we'll be teaching her soon. But Ashling, thank you so much. I don't think we have enough time, but we'll check it out. Remind me, we'll do it first thing tomorrow. We've got tomorrow morning and afternoon office hours. So great job right there. Or I might be able to send you, email me and I'll send you a video because I think I've done it before. But I will do it during live office hours too this semester. So check it out. So when we have a predictor and we have a response, you're welcome, Ashling. 100 points for all that positivity right there. I love it. The price, when it says response, and I don't like that wording, response means what we're interested in. That makes it the Y variable. Just basically telling you price is the Y variable right here. Predict or means it's going to predict something, which means it's the X. It's an explanatory. I call it the explanatory. This would be the predicted. This is the predictor. So you've got your predicted variable and the one that predicts it, the predictor. Don't love the wording. But just important to know things people might say. It's important to know synonymous words. So I'm going to use, for my example, I'm going to go right over here to the data. Where's my data? Here's my data, my 482. Make sure you have your sample 400. I'm using different stuff right here. I am going to go to Analyze Fit Y by X. Just showing where it's at. Analyze Fit Y by X. It'll be at the top of the screen or the top of the window, Mac or PC. Analyze Fit Y by X. And then here, I am going to predict somebody's, let's go here, how much people read. I'm going to predict how much people read. That's the response. So look, it says response right there. So that's, hey, that's good. It says response. That's the response. That's the Y variable of interest, the response. And then we go here to X, which is the explanatory, the predictor. And we're going to use someone's high school GPA to predict how much people are reading. Once we hit OK, we are presented with a scatter plot. A scatter plot is a bivariate visualization of, we've got right here the graphic. Scatter plot is a quantitative bivariate visualization. Look where it says quantitative right there. And you'll see scatter plot in that box telling us that's what we get. Oh, yeah, we'll get into that, Casey. You bet. Great job, Casey. Excellent work. Let's throw some points out right there. You got it. And so with this right here, we're going to go to the red arrow. Red arrow is where your options are at in Jump. And with the red arrow, you will go to fit line. This will fit the regression line making the predictions. Once we get our regression lines, take a look at it, and we want to take some good screenshots. Ooh, this is not that great of a regression line. I'm going to fix this up. Yours will not need this sort of fixing. I'm going to change this to weekly hours reading. Yours does not need this. I don't know. I don't think you're asked to change decimals. I'm making this look easier to read for us talking through it here. This is the regression equation right here, and you will need... I'll show you what your screenshots will be. You do not need the analysis and variance section. Close that off. You will need the parameter estimates section, and you will also need, let's grab one more thing, and this is the one thing to make sure you have, the plot residuals. So we should have all of our output right here, and you can get it all on the screen. Don't make it look too crazy, but if you zoom out, we can probably do this. I'm hitting Control-Shift-. You can get it all on the screen on one screenshot, probably. Let's see if it looks crazy or not. I'm zooming out, and we're about to get it all on one screen. I'm going to make the plot smaller here now that this is like this. And that right there. You can do it in multiple screenshots, or you could do like I did and zoom out. This should be pretty good right here. No one should complain. I've got a little bit of white space right here, but I want to show you that your screenshots, make sure that's on the bottom. We got it. Looks a lot better. Everything is decently sized, is legible, and you can get this all one screenshot. Now we're going to go through here and take a nice screenshot of this right there. And just to reiterate, do not forget to go to plot residuals. You could do this in multiple screenshots if you want. Just take nice, good screenshots. So right here, I've got the plot residuals, which gets you this first plot down here. Let's go back to our Word document and drop this in, and we're going to make it smaller right here. Make sure to grab this. Do not grab these. This changes the aspect ratio. Don't grab these things right here. That's a bad idea. Never, ever, ever change images by doing that unless you're trying to change the way it looks. I'm going to center it, and I want to point this out. This is a nice, clean screenshot right here. So we have a great screenshot. We're good to go. Don't make it too large. Don't make it too big. Probably something about that I'm thinking is just right. There's variations in how large or small people are going to make it. But if you think if someone's reading this on the screen, you can still see the output. Like, can you read that output? Maybe say a little bigger, Brian, a little bit bigger right here. There we go. So now we get down to the 4 conditions. I might even do this, since this is taking up most of that page, I'm just going to go here and do this. I'm just going to put it all on the first page right here and say, there's my output. And I'm going to go here to the second page and start interpreting on the second page. What are our 4 conditions, which I think it asks? What are our 4 conditions right here? It says your screenshot needs to include this, all this good stuff. We've got it. We did good. Name the 4 conditions and give evidence on whether your regression plot fails or passes the conditions. So what are the 4 conditions for regression? QQ, straight enough. No outliers. Plot doesn't thicken. Now, hopefully the graders know I like to call it QQ for 2 quantitative variables. I'm not going to, but what I would do, I'm just saying, you just take these right here off the side and just drop those in right there. Go right here, put it over to here. Oh, what's it doing? Try to get it nice and neat right here. Sure, we'll just copy it like that. Quantitative variables condition. Straight enough condition. No outliers condition, plot doesn't thicken condition. Sure, just do that. And then we go here, and we give an answer why. So we need to talk about all of these. We need to talk about all these conditions, why they're met or why they're not met. So this is a part I'm not going to do right here because I want you to go through and think, how would you explain? And I would probably do this. Oops, don't want it doing that. It is met. You know what, I'll do this one. Is met because we have 2 quantitative variables. Both GPA and weekly hours reading are quantitative. This is what you want to do right here, and this is the way to practice for the test. And it's very clear and easy for the grader to see you've got the 4 conditions. Does this make sense right here, Casey? With this right here, if you're very clear, like, is the condition met? Like, saying what the condition is, it is met because we have this. And then for the next one, like, we need a straight line to well approximate the relationship. It looks to me like, if you take a look right here, in truth, I don't think this one has issues with straight enough. I see some extreme outliers, like someone who has a 3.0 GPA and loves to read 45 hours reading a week. It means they read for at least 2 full days. Or if they read half the day, they read for 4 days completely. That's a lot of reading. Maybe they do it. Maybe they do it. That's over 6 hours of reading a day, 6.5 hours of reading a day every day. Maybe they love reading. I don't know. And then we see another extreme outlier over here. So I think there's issues with outliers. Does the plot thicken? Yeah, we got some plot thickening. Towards the center of the plot, it's a lot thicker than elsewhere. Does that make sense? What you should be covering inside of here for these conditions. For these conditions, make sure it's very clear. I might even go through here and do something like this because that would make it very clear for the grader. And then if I go down here, oh no. I'm sorry, Mohammed. So this is like, once again, top tier way of doing it. You're making the grader's life nice and easy right here. So when the grader is going through and doing this, you don't have to do little things like this, but man, I'll tell you, when I'm grading papers and someone makes it so clear, like It's very clear to see the 4 conditions right here. It's very clear to see where they're pointing out when things are not met and why they're not met. Pretty easy to grade this. You're like, oh, you just look at it and you're like, yep, met, not met, yep, good. Okay, got it. You understand what the condition means. You're good. You just read through, you're like, yep. So those are the conditions. Make sure to go over the plot doesn't thicken. That means we want to see even thickness throughout the plot. Just to review the notes from today. You want to see a plot that looks like this right here. The more it looks like this, and if you make this a residual plot, it would just look like this. So that's what you'd want to see in a residual plot. You do not want to see plots that look like this or a residual plot that looks like this. A residual plot is just the same line but flat. So this would be good and this would be bad. We do not want the plot to thicken, as in this is good. We don't want this down here. So we probably see some plot thickening in mind, like especially in this area towards the center. So I'd say that. It's not that because in the center of the graphic around 3.5 to 4, we see a thickening of the plot indicating the model's strength is changing. This is not good. Now, the last part of this right here, I believe, is interpretation of the coefficients. So we got the 4 conditions, and then we have the intercept, the slope, and then we want to know if it's statistically significant. So once again, I do go over these in the video, but I want to point something out. I'm going to take this away from here. We have some really great interpretations, and we'll be finishing off in a second right here. And let's take this and bring it over here. So when you interpret these, when you interpret your X and your Y, and we'll make it smaller so we can see both things at one time. Put this over here, and put this over here. When you interpret your X and your Y, you need to give context. If you don't give context, you will do very poorly. Not have a good time. So we see right here that the y-intercept is when someone's high school GPA is equal to 0, which is worth mentioning. We don't have individuals with a high school GPA of 0. That's an extrapolation of the model. We'd expect their weekly hours reading to be 6.09. When somebody's high school GPA is equal to 0, we expect their weekly hours reading, which is the y variable, to be equal to, and this is B0 right here, 6.09. We don't have any data down there, so although people can have a 0 high school GPA, it's a little bit illogical, but still possible, but it's an extrapolation of the model. That extra is not needed. I would say if it's illogical, but you can, I guess, have a 0 high school GPA and read 6 hours. It's not negative, so you can read 6.09 hours on average. The slope interpretation right here, and I'm going to add this on. Some graders are a little bit too wanting to take off points on this. On average. I'm going to literally tell Terry, let's not put that on average thing here, but I do see graders take off. And I probably should just start writing it, because I've seen graders take off, but I don't care for it because we say expected. So that should cover that this is on average, because we expect, not saying it will. Don't say will. Will should lose points here. Slope interpretation would be, for each 1 unit increase in someone's high school GPA, we would expect their weekly hours reading to increase by 0.5. So we are predicting someone's weekly hours reading. So for each 1 unit increase in someone's high school GPA, we expect the weekly hours reading to increase, because it's positive, line goes up, by 0.5 on average. Just throw that point on average there for the graders who are angry about not having that. So next we have r squared, where we have, oh, this is nothing, about 0. That's about 0. You should times this by 100. So take your r squared value. It's a percent out of 100, and it's not correlation. So that is a percent, 0.09% of the variation in weekly hours reading is explained by someone's high school GPA. Last but not least, we can see if the line is statistically significant, and that is in our output all the way right here. This tells us whether or not our line is statistically significant. Do not confuse it with the intercept. We want to look at the slope, which is the XY relationship. Interestingly enough, this is also in the analysis of variance, same p-value right there. So you can see right here the 0.5073, which is the p-value of the model, is the p-value of the ANOVA right here, which is good for 320. So this is not a statistically significant model, and it's probably because the line is mostly flat, telling us that the relationship that weekly hours reading has to someone's GPA is just likely by random chance. Well, that's got it, everybody. Don't want to play that song for too long. Get copyright claimed by Monster Cat again. I almost licensed it. Almost gave him money to play it. Didn't do that. We will be back. If you didn't get your question answered, let me know. We'll be doing more questions next time. Going to be teaching class here in about 15, 20 minutes. Going to grab a snack, probably some yogurt. Excellent stuff. Grab your snack. Grab some more coffee. Everything's good. Water's still turned off because they turn off the water every other week at our apartment complex. Don't know what's going on. See everybody later. Bye for now. Bye. You got this.